Hello. Today we're going to be discussing the Chapter 9, Managing Linux Processes. This chapter is a little bit, to some people that haven't used the Linux systems as much, maybe a little bit confusing. One of the things that we have to understand from the beginning, everything running in any system, whether it be Windows, Linux, Apple, everything has a process. And in that process, we're running, something's happening. These are the objectives for this chapter. The Linux processes, when we look at the word program and processes, sometimes they're used interchangeably. To some greater or lesser degree, it's okay to do that. But when we look at what a program is an executable file on a hard drive that runs when you execute it. A process is a program that is running in memory and on the CPU. In other words, it is a process that is a program in action. So there's kind of a little bit of twist on words or a little play on words there. Some people get confused with it. A program, if you're talking about a program is really an executable file. It hasn't been executed yet, but when you execute it, it's actually running. It is a process. So if you start a process while logged in into a terminal, the process is labeled a user process. A system process that is not associated with a terminal, in other words, with a specifically logged in individual, is called a daemon process. Processes that are typically started during system startup or started manually. Normally when we talk about a process that started manually, we're talking about you have to have the root user systems or super user login process at that time. It's not associated with an individual user other than a root. Most daemon processes provide systems services. Every process has a unique process ID referred to as a process ID or PID that allows the kernel to identify it uniquely. Each process can start and an unlimited number of other processes called child processes. Each process has a parent process and a parent process ID. The INIT daemon has a process ID of 1 and a parent process ID of 0. All right, now, whenever you start up a system, the system's a process starts. Now, in order to run that specific program or process, there may be several other child processes that have to be initiated or subroutines that have to run in order for that one individual parent process to run correctly. All right, and this is the only thing. This is the way we're looking at it. When you have to look at something that runs and then depends on something else that runs concurrently. All right, now this diagram, when we look at it, this is a figure. It's on page 392 of your textbook. It's a parent and child processes. Now, to view processes, you can use the PS command. Without arguments, the PS command simply displays a list of processes that are running in the shell. You can add arguments to enhance what you view on the screen. As you can see by this slide here, the process flag F indicates the particular features of the process that you will use this in later labs. I'm only going to give you a couple labs to do at the end of this chapter, and it's just basically going in and initiating some of the commands that we talk about today. Excuse me. Process state, or S column, is the most valuable because it indicates what the process is currently doing. The zombie process is a process that has finished but the parent hasn't yet released the child process. Process priority is used by the kernel for the process. It is measured between 0, which is the high, and 127, which is the low. You'll notice that in this chapter, the lower the number, it's the higher the order in which it simply occurs or has priority. Nice value can be used to affect the process priority indirectly. It is measured between -0 and 19, the -0, or -20 or -20, and 19, -20 being the greater chance. When the PS3 command is used, it displays the lineage of a process by tracing its PPIDs to the INIT or INET daemon. Again, the common options to the PS command. The top command displays an interactive screen listing the processes organized by processor time. Processes that use the most processor time are listed at the top. The rogue processes are used processes that have encountered an error during the execution of and continuously use systems resources. They appear at the top of the listing produced by the top command. You can also use the top command to change the priority of processes or kill them. The kill command is used to terminate a process, and the kill command can send 64 different kill signals to a process, each of which operates in a different manner. And the kill command with the -L option can list or could display a list of kill signals, names, and associated numbers. This is the table 9-2. It's the common administrative kill signals. Some processes have the ability to ignore or trap certain kill signals that are set to them. The only kill signal that cannot be trapped by any process is the SIG kill. This should only be used as a last resort because it prevents a process from closing temporary files and other resources properly. When we think about using a kill command, it's kind of like going into Control-Alt-Delete in a Windows system, and when you look at the task, which things are running, and if something is running and yet can't, you go in there and click onto it and hit end or delete it, and it doesn't stop that process, it continues to run. When we try to end or terminate a process from running, and that process continues to run, we can't get it to kill, it may be running back there in type of a rogue manner, and the problem with it is that it's not being able to close out all files properly. When we go in there and just terminate and use this command, the SIG kill, it will terminate the process immediately. But the problem is, again, it doesn't close those files, and we could end up with corrupt processes after a while if that happens very often. You probably want to look in there and see why those are not terminating properly, and then you could go in to look at some of the archives and see if that will help you in any way. Kill all command kills multiple processes of the same name simultaneously. In other words, the kill command works similar to the kill command in that it takes the kill all command. I'm sorry, in that it gives a kill signal as an option. However, it uses the process name to kill instead of the PID. This allows multiple processes of the same name to be killed in one command. Linux has three main types of executables: binary programs, shell scripts, and the shell functions. Examples of binary executables are the ls or list command, find, and grep command. Examples of shell scripts are the cd and exit commands, which are built into the bash shell running in memory. When executing compiled programs or shell scripts, the bash shell that interprets the command you typed creates a new bash shell. This new subshell is known as forking, and it is carried out by the fork function in the bash shell. The new subshell executes the binary program or shell script using its execute function. After execution, the new subshell uses its exit function to kill itself and return control to the original bash shell. This is the picture in your textbook. It's figure 9.3, process forking. Excuse me. The original bash shell must wait for the command in the subshell to finish before displaying the shell prompt to accept new commands. Commands run in this fashion are known as foreground processes that are in the front. Alternatively, they omit the wait function by appending an ampersand character to the command. And commands run in this function are known as background processes. When a command runs in the background, the shell immediately returns the shell prompt for the user to enter another command. Now, think about it this way: if you're in a terminal window and you're typing a command, if the command that you're typing is executed and you're automatically returned back to a shell prompt, to the terminal prompt, so that you can execute more commands, then it's the bottom process here. It's background processing. If you execute a command and you're not returned to the shell prompt, to the terminal prompt, that's a foreground process, and then you have to enter something else in the display. The jobs command is used to view the background jobs ID, and to terminate background processes, you use the kill command. After a background process has been started, you can move it to the foreground by using the foreground command followed by the background jobs ID. You can also send a process to the background with the background command. Control and using the Z command, Control Z combination assigns the foreground process a background job ID that is then used as an argument to the BG command. Process priority. Time slices the amount of time is the amount of time a process is given on a CPU. More time slices mean more execution time on the CPU. It executes faster. Usually is measured in milliseconds. Some of the advanced utilities that we have in some of our programs, like Linux for Linux servers, and also for network servers, Novell network servers, we can actually go in there and monitor that, and we can see and change with some of these other utilities the time slices that processes have, and if something has taken too much time or processor time, we can go in there and make adjustments and change that. Now, this is getting into real technical kinds of things, and in order to on servers, you've really got to have a pretty good idea of how much time you want to allot for processes. Process priorities dictates the number of time slices a process gets. The lower process priority number is likely to get more time slices. You cannot change the PRI value directly. You have to set the NI to indirectly affect priority. Again, a lower number increases time slices. It starts with an NI of 0. Use the nice command to change a process's priority as it starts. Use the renice command to alter the NI of a process after it has been started. Processes are started by users executing commands while logged into a terminal. There may be times when you want to schedule a command to execute at some point in the future. You can use two different daemons to schedule commands for future execution. Use the AT daemon or ATD, and then you can use the cron daemon, CRON daemon. The command would be CROND. The AT daemon is the system's daemon that executes tasks in a future time. The CRON daemon is the system's daemon that executes tasks repetitively in the future. The AT daemon schedules commands and tasks to run at a preset time. And you can see here on the screen where you can actually go in and set those commands up. The AT daemon uses the current shell's environment for execution. Again, the CRON command, a cron command, is used for scheduling repetitive tasks in the future. The cron table configuration files specify when commands should be executed. It has 6 fields separated by spaces or tabs. First 5 specify times to run the command, and the 6th absolute path name to the command to be executed. User cron tables represent tasks scheduled by individual users, and the system's cron tables contains the system's tasks. And here you can see the in the first figure 5 or 9.5, the user cron table, and you can see the different times that you can actually set. Notice the numbers 1 through 5, which actually schedules the minute, hour, day of month, and the day of the week. And then the day of the week would actually be scheduled from 0 to 6. And then the bottom of the sample user cron entry, cron table entry. All right, that's it for the Chapter 9 video presentation. I hope you have a great week, a wonderful week. If you could complete Project 9.1 and 9.2, all assignments are due on Sunday, April 1st at midnight. Thank you and have a wonderful week, and hope everything goes great.